So, in the last class we were telling that okay, what's this issue of actually computing the integral, and I told you that this computation is not so simple even for very simple situations for non-negative functions, because I told you about these bounds that we have given in terms of the area, the upper estimate and the lower estimate. Could we use that to do something? So, I am now asking you to evaluate the integral. It could be x square dx. So do not get too much worried about this dt symbol come here, it's a symbol actually. We tend to give meaning to this. It is basically telling you a continuous sum of the function values, the length, the function values into very small base, and it is infinitesimally small. So, in that very small base the functional value does not change. So, that is the length of the rectangle that you construct with the base dt. So, that is essentially the meaning, is a sum in that sense. So, don't put too much thinking about it, dt kya hai, that sort of, sorry, what is dt and all those sort of thing. So, now I want to evaluate this. Anybody who has studied for entrance exam would say, oh, this guy is crazy. I obviously know the answer. This is simply t cube by 3. इसमें बड़ी बात क्या है? Sorry to speak in Hindi, but in general it would be okay. What's the big issue about it? Why make such a fuss? Please understand that we have not yet introduced antiderivative. We have not introduced many other things. We are in a primitive state of affairs where we are simply telling, we are possibly in that very old classical setup, we are simply telling that this is a number, this is an area, this is just a symbol of that number. Now, how will you evaluate such things? I want to again assure you, and I want to tell you that this was not done overnight. It needed a lot of work. And the upper estimation and the lower estimation business works, and that is actually used. Now, let me tell you that if this way of thinking, that we are taking these historical steps, because many big mathematicians, as I told you, Cauchy, Fermat and all these people, they have actually given a lot of time to evaluate such things and then actually generalize it into a formula. So, things have not come up overnight. Please understand this very simple thing. So, once if you have a table of formulas, it is very easy to write the formulas, put it down, solve problems in the exam without an understanding of the real meaning and the real issues at hand. So, that is what this course is supposed to do, to tell you what calculus actually is, what are the real issues at hand. So, here I am looking at the part of the graph y equal to x square. So, this is 1, say, and this same length, this is 1. So, this is 0 and this is 1. So, this is y equal to x square. Now, we want to actually now divide the, I will divide this 0 1 interval each of length 1 by n. Here b is 1 and a is 0. So, its step length h is 1 by n. So, the first point here where we cut is 1 by n, then 2 by n, and so in the middle I will have r by n and r plus 1 by n and go on. Now just I will concentrate on this part and look into this area. What does this area mean for this function? It means that we are essentially, if I write it in this form of the symbolic, the integral, it is r by n to r plus 1 by n t squared dt. But let me now construct the upper estimate and lower estimate of this area. The upper estimate means I construct a rectangle of this height. So, which overestimates it. So, the rectangle of this height is, so it will be what? It will be in this 1 by n is the base, and then this is what? This is the length is nothing but the functional value. So, the maximum is achieved at r plus 1. So, the maximum is achieved at r plus 1, the functional value is r plus 1 by n, sorry. So, it is r plus 1 by n whole square. Similarly, here on the other side it would be 1 by n into r by n whole square, because here now the area we will be looking into this rectangle. This will be, one is the upper one and one is the lower one is that this one. So, here the lowest value of the function on this range is r by n. This is a increasing function that you clearly observe. So, there was a little mistake here. I just while I was speaking very fast, I just forgot to give the limits. So, this is all known to you in most of the cases, but let us forget about this. Do not think you are taught and having limits. So, you are just in the situation where you are doing the real math, you are actually seeing this estimation and trying to understand how to evaluate this integral. So, if I now sum it, if I sum this where r varies from 0 to n minus 1 in one case, and so when r varies from 0 to n minus 1, then if I sum these up, this part up, these small parts, they will give me the whole curve from 0 to 1. So, basically I will have summation r equal to 0 to n minus 1 by n cube r square by n cube, and this is less than equal to, but if I sum these up, this will be nothing but the whole area. So, it is the integral so it will be 1 by n cube so this is the summing. So, n is not the issue, it's n is fixed, so you are varying. So, basically you will have 1 by n cube to 0 square plus 1 square plus n minus 1 square, and this is less than equal to 0 to 1 t squared dt, and this is giving you 1 by n cube 1 square plus 2 square plus n square. Now, here you have to use a very important formula which is taught at the high school level. But you see, in those days it was not an easy thing to actually figure them out. This was research mathematics. So many of you would possibly know. So you see the amount of stuff that has been used here. So this is 1/6 of n plus 1 to 2n plus 1. So here if I write it down, it will become 1/n cube into, I am writing for this part, the left part. So it is n minus 1 into n and 2n minus 1, and this is less than the integral one by n cube into n into n plus 1 by 2n plus 1. Now what I will do is a simple trick. I will divide this n by n cube by n square by n. So I will have 1 by n square in the denominator, and then I will split 1 by n square into 1 by n into 1 by n, and then divide 1 by n with this and 1 by n with this and 1 by n with this and 1 by n with this. So I will have 1 by n square n minus 1 into 2n minus 1. This is less than equal to 0 to 1 t square dt. One by n square into n plus 1 into 2n plus 1. Now as I told you, I will split it up, and hence let us come to this side of the expression. So now here we are coming again from here. So from here, if I just give a hashtag, so this language is understood by everyone, hashtag. So here I will have, if I divide by n, 1 minus 1 by n, if I divide by 1 n this part and then this part, and 2 minus 1 by n. This whole thing is less than 0 to 1 t square dt, and this itself again is less than 1 by 1 plus n and 2 by 1 plus n. So 1 by 1 plus n and 2 by 1 plus n. Now you take the limit as n tends to infinity. So what we have missed is somewhere 1 by 6th here. So 1 by 6th has been missing. So I have to put 1 by 6th here. 1 by 6th. So just applying the formula 1 by 6th. So here also it will be 1 by 6th. Here also I will have 1 by 6th. So now if I take the limit as n tends to infinity, this will go to 0 1 by n, this will go to 0 1 by n things. So it will be 2 by 6. So 2 by 6, which is 1/3, is less than equal to 0 to 1. So this is independent of that n, is less than equal to, here also it is 2 by 6, which is 1/3. So which means what? This means 0 to 1 t square dt is equal to 1/3. Now I will tell you that I will give you another integral. I will show you another example how geometry can help, and without anything I will do something interesting. Without much help of any of this sort of working, and you will see the number pi again appears in front of you. I will immediately write a more complicated expression. I ask you to evaluate the integral. What does this give me? What does this 1/3 tell me? Does 1/3 tell me anything? Is there some information in there? Nothing. It just tells me that this is the area number. So here we are just figuring out the number. So integration is just a symbol which is actually a number, right? So I ask you to directly a much more complicated, not simple function. You say, oh my God, what's this? Suddenly that's a change. You have to observe that this function fx if I am keeping x between -1 and +1, this function is always non-negative. And so whatever I have learned can be applied here. But do I need all these strategies to evaluate it? The answer simply is that you do not need any of these strategies that you have just learned to you do not need any of these strategies to do it. Because you see, I always want to emphasize, it might be my view or that is the way I can understand things, that mathematics cannot be learnt well without visualization. Mathematics is all about visualization. Geometry is at the core of things. So here what does this symbols, if I have this function y equal to √1 minus x square, this simply means x square plus y square is equal to 1. So it is telling me to find the area so this is a circle, but I am only looking at x between -1 and +1. So between -1 and +1. So y can have plus minus this. So I am only looking at the positive part instead of if I, so here I will have y from here, y equal to plus minus √1 minus x square. I am only having the positive part because I am not put the minus sign. So if you just put the positive part, 1 minus x square obviously has to be non-negative, otherwise you cannot evaluate the integral, cannot evaluate the square root. So what does it mean? What is this integral telling me? It is telling me that this is nothing but half of the area of the circle. And we have just learned today that area of the circle, pi is a constant we know, is, so this is nothing but, if, so this is +1, so this is x, so this is the point +1 0, this is the point -1 0, so this is with the center 0 0, so this is a circle of radius 1, just from this equation, this is a circle of radius 1. So its area is pi r square, it is pi, but I am only looking at the half part, it is symmetrical, because I am just evaluating the positive part. So this is nothing but pi by 2. So pi by 2 is -1 to 1 √1 minus x square dx. See, such a complicated integral looking integral can be immediately figured out. Similarly, if I for example, if I take minus a to a √a square minus x square dx, it is the same thing. Now the radius has become a, so it becomes pi a square by 2. So you see, complicated functions are immediately, the integral is evaluated once you know some geometry. Now I can use this thing to evaluate the area under an ellipse. So you see, we are getting more into more complicated stuff without much effort once the geometrical view is clear. See, all these things that you have written, they are all geometrical views. And then later on, this is a geometrical view coupled with a limiting process, and that is allowing you to evaluate the areas. for example, if you have an ellipse, sorry, so these are the two foci, right, focus of the ellipse, and let me write the answer. So this is A0 and minus A0, and this is B0, sorry, 0B and 0 minus B. So this is the major axis and the minor axis, and the equation is x square by a square plus y square by b square is equal to 1. But I want to evaluate this area, but what we are exploiting, not only we are exploiting this fact that we know the structure of the equation, I know what sort of curve it is giving. Basically now I want to find this area. So what sort of curve what sort of things I am exploiting? The key feature that I am exploiting here is symmetry of geometrical objects, and because of that I can simply write this is half of that. The symmetry of the geometrical objects is playing a very important role, and symmetry is really a very important concept in the natural sciences. So here what I do, so I will just take this part, the upper part of the ellipse. I would not bother about the next bottom part. I just know facts about non-negative functions. The whole notion of integral is valid for me when the function is non-negative. So I will look at y is equal to b into root over 1 minus x square by a square. So basically now I am integrating from minus a to plus a, b into root over 1 minus x square by a square dx. So this, so area of ellipse, this is my area of the ellipse, and what is this? This is nothing but integral minus a to plus a, b by a into root over a square minus x square dx, of course. And again, you know, now we do not know what would happen if there is a constant in front of the function. That is what would happen. How do I evaluate this? See, the best intuitive way to look at it is in this way. How will you figure out? Of course, we will do more details about all this, but the way to figure this out is the following. So, you know, if you move the function, you scale the function by c, then your maximum value and your minimum value is also scaled up by c. So, it will have say c times m into b minus a and c times n into b minus a. Now, you already know that n times b minus a is less than or equal to integral a to b fx dx, c times is capital M times b minus a. So, if I multiply by a positive number c, so I am multiplying by a positive number, here b and a are positive numbers. So, if I multiply by a positive number, what is happening? You are getting this equation. So, once you have this, you know that these two equations look same. So, possibly and intuitively, and it is correct, that you can immediately conclude that c of f of x dx is equal to c times integral fx dx when c is positive. So, this is simply an intuitive idea. It is not that I have not done any rigorous proof there, rigorous proofs comes later on. This is just an intuitive idea. Okay. So, once this intuitive idea is known, what am I supposed to do? So, I know that that is what I have. So, I can simply write this to be B by A minus A to A root of, sorry, so area of the ellipse is not this, area of the ellipse is half of the area of the ellipse, because we are just considering this part. So, we are just finding first the area of this part, then we will make it. So, half of the area of the ellipse is what we are getting. So, please note this, sorry. So, this is nothing but minus A to A square minus x square dx, and that is what we have already evaluated, pi A square by 2. So, the answer here is B by A into pi A square by 2. So, half of the area of the ellipse is equal to B by A into pi A square by 2. So, area, so A cancels because these are positive numbers, area of the ellipse is simply pi AB. See, you have done everything without any effort, and this is where the beauty of mathematics lies, that a lot of things, if you viewed in the right way, can be done without effort. There are 3 minutes to this lecture, and so I will not start doing anything new, but I will ask you to go back home, look at the definitions that I have given and prove something which is interesting. As Corner mentions, that there is something about area. What is that about areas which the Greeks didn't know, but that thing we know about the integrals, and that is the following, that if f and g are non-negative functions over AB, non-negative over AB, then integral A to B f plus g of x dx, that is fx plus gx basically, that is same as separately evaluating the two integrals and adding them. So, I would like you to prove, this is something is immediately interesting which the Greeks didn't knew about the areas, that if you add these two areas under two curves, the new area that is formed is actually area under the sum of the curves, the sum of the functions. The curve that is generated by summing the functions, the area under that is the area of this sum of these two in component ones, and that is the key thing that which the Greeks had no idea about. And so, it tells me much more about areas. This is a big statement about areas. It is just not just a sum kar diya, such as I have written a sum and I forget about everything. So, I would like you to go back home, look at the limiting definitions, and can you use the limiting definition which I had given earlier, A plus NH, that form, and show that this is possible. Well, those will come in the next lecture. So, tomorrow's lecture we will talk about how would I define an integral when f need not be positive, need not be non-negative, when f could be anything. What would be the answer? How would I do it? We shall do that and many more, and we shall get into this whole idea of antiderivative through the notion of what is called the fundamental theorem. So, that will be the third version of this talk. So, here we are doing things in a slow manner, but you see how things are getting evolved, that once you know what it means, that what area means, a lot of things can be achieved. That if the integral actually represents the area, lot of complicated looking integrals can actually be resolved. Okay, so we end this here today, and after tomorrow's class, in the next week, next week's lecture, I think the 5th week, we will start talking about Riemann integral. Riemann, for example, one of the greatest mathematicians of the 19th century, famous for introducing Riemannian geometry. I will tell his story a bit, because also he talks about the Riemann hypothesis, which might not be understood by most of you, but okay, some stories can be told. He thought about this particular case. Suppose I have defined a function, say from 0 to 2, and from 0 to 1 it is 1. So between at 1 it does not take any value here. At 1 it takes the value 2, and then at 2 it does not really take any value. So here the fx is equal to 1 when x is this, and is equal to 2 when x is between 1 and 2. Now, does this have an area under? This is a discontinuous function. You have already seen some discontinuous functions. Does this have an area? You can say, okay, this having area, this, if we say that this has area, we are actually making a very big statement. And those who actually, if somebody is watching this, who has actually advanced math training, would really know that we are talking about that if there are some so-called set of measures, there are few points at which the function is discontinuous, you can just disregard it. This function is a bounded function, it is not an arbitrary one, its values are bounded. Now you can say, okay, does not matter, why we bother about this one point, what is the problem? Take this area, this rectangle, and take this rectangle and sum them, that define that to be the area. So if this is a function, how do I then evaluate what meaning then I give to this? Because till now we have been talking about nice continuous functions, we are not talking about anything else, but now we are talking about something else. We are talking about functions which could be discontinuous, and that will start talking in the 5th week, and this will give, this story would be the story of Riemann integration. Basically it is or Riemann, I am forgetting the spelling, must really this. Riemann integration. And Riemann, by the way, this Riemann integration came in his thesis. So he thought that he conquered Newton's game by showing that okay, most of the functions which Newton couldn't do anything about, or Newton and Leibnitz, I have a way to integrate them. Because he was only talking about bounded functions, and every continuous functions are bounded, and so but every bounded function need not be continuous. Here is straight an example in front of you, and he said, okay, so I have one up Newton. Then his PhD supervisor, Gustav Dirichlet, gave him a small function when fx is equal to 1 when x is rational, and fx equal to 0 when x is irrational, just before his PhD examination, and told him, just see whether this is you can integrate it. It was not integrated, though it was a bounded function, it was not integrable in the sense of Riemann. And so the story of integration does not stop with Riemann, it goes on to be finally in 1902, who a French man called Henri Lebesgue, I would say, but the French would call Henri Lebesgue, but the things H and R are silent, I are silent. So this man Lebesgue would in 1902 write a thesis where he looks into the difficulties of the Riemann integral and devises a new way of looking at computing integrals. He wants to integrate functions or give meaning to the area under curve of functions which are not even having area under the Riemann sense then. So you see the whole notion of area is getting changed. What do we mean by that? So how for various types of functions. Now what he did, Lebesgue, so this story has to be known also, even though I won't be teaching you, that he did a completely different thing. In his thesis he said, okay, these guys, Riemann, Newton and all these fellows are actually partitioning the x-axis, I will partition the y-axis. Can then I do something improvement? He just changed it, and that is exactly what he does. So, that story I will tell at the end of this story. So, but there are few integrals which might not be Lebesgue integrable, but most of the integrals are Lebesgue integrable, and it is till now the official integral of mathematics. But there is some unknown, not so very famous mathematician called Kurzweil and Heinstock, who did a little bit of thinking that could I improve the Riemann integral in such a way that those functions which were not Riemann integrable in the sense of Riemann can now become integrable in the sense of Riemann. That is called the generalized integral or the Heinstock integral or Heinstock-Kurzweil integral. So, where I will tell this fact a bit when we talk about Riemann integration, where those functions like the one which Dirichlet gave was not Riemann integrable becomes Riemann integrable in this generalized sense. But unfortunately for some reason or the other, because this is all is a question of tradition in mathematics, that Lebesgue has entered into the bloodstream of mathematicians in such a way that it is very difficult to get him out and accept the generalized Riemann integral as one of the top ones. So, it is good to know some story about things. So, with this whole idea of integration, which you might, or just finding area which might look very trivial to many people outside mathematics, is actually very deep and a very interesting thing. So, I hope you enjoyed the lecture, and next time we will start talking about other things, but the Newtonian spirit would be maintained, and till the next week when we will come to Riemann's famous integration idea. Thank you very much.